All right, so I see a lot of people connected from all over. Just before we go on, can you kindly just type in the chat box where you are reaching us from? I know some of us are from Pakistan, some from India. I think we have Algeria. Yes, I think we have that here too. So just for interaction's sake, you can just type where you're from. You can put it in the chat box. Okay. All right, you can see that. Can drop me more. I can see, let me just quickly greet some people. I can see Sad. I can see Donald D. I can see Nas. Okay. Olawale from Nigeria. Okay, I can see you. I can see oh yes, Nas from Algeria. Patel from India. I can see you. All right, so we have a lot of people here connected from all over, and I really want to appreciate you all for taking out time to be in this webinar today. Um, like I said, we are dealing with gas pipeline, line sizing, and hydrate prevention. I am your host for today, and my name is Afolayan Oluwaseyi Emmanuel, but you can all call me Emmanuel. All right, so I'm going to be starting with the PPT before we go into the simulation proper for today. All right, I can see you from Sudan, Mohammed. From Sudan, I can see you. Okay, Mahmoud from Sudan, thank you. All right, so we are going to start today. Yes, I see another person from Sudan. All right, so let me share my screen with you all. Okay, so we are going to try and keep this call on this webinar is supposed to be an hour 30 minutes. So what I want you all to do for me right now is turn off your mics. Any question you have, any doubts you have will be coming after the okay, we're going to put it into two parts. After I'm done with the PPT, I will take any question for that, and then immediately after that, I will go in just for 5 minutes. And after 5 minutes, I'll be going into the simulation proper for today. All right, so you all should just turn off your mics, and once I'm done with the PPT, take 5 minutes question, then we move into the simulation proper. All right, so here we go. So we go with we are dealing with gas pipeline, line sizing, and hydrate prevention. All right, and what this is all about is just to help us understand gas transportation and the possible damages and the causes of these damages that could happen in your gas transportation pipelines. All right, we're also going to be doing line sizing, how to properly size your pipes during gas transportation. All right, so it could be um, in the air, that's you could pass the pipe in the air, you can pass it underground or in water. We're going to be dealing with all of that. And then this is just to show you how it is being done using ICE simulation. All right, so let's go. We have this is all about mastering piping systems, line sizing in HYSYS is essential for efficient process design and optimization. This presentation explores the fundamental concepts, tools, and methodologies for modeling complex piping networks, calculating pressure drops, and determining optimal pipe size for safe and reliable fluid transport. All right, so what is gas pipeline and transportation? So your gas pipeline is a network of pipes for transporting natural gas from along a very long distance. It's crucial for energy supply, connecting production sites to cities and industries through gathering, transmission, and distribution systems, often requiring a compressor station to maintain the flow. You have a network of steel pipes that moves natural gas from production sites, which is the wells, through long distance, that's the transmission lines, often underground or under the sea, to distribution systems, which then delivers it to homes and businesses using compressor stations to maintain pressure and corrosion protection. For that, you have to do coating or cathodic protection for the integrity, making it the most economical way to transport gas over land. All right, so the idea of your gas pipeline and transportation is to be able to move gases from different gas wells, often with the aid of compressor stations. All right, we have different compressor stations located at different places. It could be at the start of the distribution line or somewhere halfway in the distribution line, just to maintain that the pressure of the gas is kept at a reasonable stage so that you can have a proper transportation of that gas. All right, so it could be done over sea or underground. Sorry, under the ground or under the sea. It all depends on what you are dealing with at a point in time. So your piping in high seas involves modeling and simulating piping systems by specifying pipe size, flow rate, pressure drops, and temperature changes for fluid being transported in the process. The software provides comprehensive tools to define pipe characteristics and predict fluid behavior under various operating conditions. So you have your pipe systems, which defines the pipe characteristics, including the diameter, the length of the pipe, the insulation, and material using the piping blocks in the simulation. So we have the pipe segments, we have the pipe hydraulics in Aspen HYSYS, which you could be using to simulate that. And you need to put in the diameter, the length of the pipe. You can also add things like elevation, depression, and all of that in your simulation for the pipe. Then you have the flow and pressure drop. So we have it calculates pressure drop due to friction, elevation changes, and fittings using the Darcy-Weisbach equation or empirical correlations. All right, so um, along the pipe, definitely there's going to be pressure drop. That's why we have compressor stations situated at certain locations to enable us to boost the pressure of the gas to enable the transportation of that gas. All right, so it is, we talk along the pipe, you'll be able to see how the pressure drop occurs, and this is usually due to friction, all right, between the gas and the pipe wall, that's the inner pipe wall. All right, then we have the pipe sizing, which imputes the desired flow rate and diameter constraints. So HYSYS calculates the appropriate pipe diameter based on velocity limits. So when we go into line sizing, you'll be seeing how to make use of velocity as well as the pressure drop across a particular distance to calculate the appropriate pipe size for your gas transportation. All right, so we have pipeline hydraulic tools in HYSYS. So Aspen Technology offers two specialized tools within HYSYS for accurate modeling of complex pipeline hydraulics. We have the pipe segment model, and the upstream hydraulics. These tools enables companies to model simple pipelines or complex networks, to simulate multi-phase flow dynamics, and implement flow assurance measure to reduce erosion, corrosion, deposit formation, and slugging. All right, so this deposit formation also deals with hydrate formation, which is part of the things we are going to be looking at today. And then to this point here, you can see our pipe segment. This is a pipe segment, and then you can see you have the length, the elevation change, the outer diameter, inner diameter, the material of the pipe, the roughness of the pipe, the wall conductivity, and then the increment in that pipe. All right, so the pipe segment model recommended for single pipelines divided into multiple segments based on the terrain or environment changes using different flow colorations for accurate modeling. All right, then we have the Aspen hydraulics. So it's part of HYSYS upstream designed for complex networks like offshore production with multiple wells and rigorous multi-phase flow mixing analysis. Okay, so all right. So the thermodynamic properties and pipe insulation. Now, one thing with HYSYS is definitely any calculation that's been done on HYSYS deals with thermodynamic properties. We have different thermodynamic models in Aspen HYSYS, which could enable you to perform any simulation you want to, depending on the process. All right, so if you are going to be dealing with things like dehydration process, um, yes, dehydration making use of things like teg glycol, that's TEG. You can also make use of MEA and things like that, or you are trying to perform a reaction process. Definitely, there are different thermodynamic models that enable you to perform these simulations on Aspen HYSYS. All right, so the thermodynamic model is one of the fundamental things we need to understand when trying to make use of Aspen HYSYS. All right, because using the wrong thermodynamic model is likely going to give you wrong results. Yes, you might have results, but those results might not be accurate because of you didn't make use of the appropriate thermodynamic model. All right, so um, thermodynamic properties and pipe insulation. So we have fluid properties, and under that, ICES defines thermodynamic properties of fluid, gases, liquids, or slurries, and calculates flow behaviors in pipes. The software employs fluid models such as the Penn-Robinson, which is one of the most common um, thermodynamic model used in Aspen HYSYS, or the Redlich-Kwon equation of state to predict phase behavior and fluid properties accurately. Then we have the heat loss modeling. The heat loss, the to model the heat loss or gain in pipes by considering insulation materials, properties, and external temperature conditions. These are critical for temperature sensitivity processes where maintaining fluid temperature is essential for product quality and process efficiency. So when you are dealing with the heat loss in your pipe, because most times it happens, especially when there is no form of insulation around the pipeline. All right, so you could have heat loss. That's why it's always good to make use of the appropriate insulator to enable you to um, transport your gas at an efficient um, process. All right. So now let's. Okay. So key factors to consider in pipeline design. All right. So there are some key factors we need to look at when trying to design your pipeline. All right. So some of the critical factors that must be considered include the pressure drop, the flow rate, the flow geometry, and changing flow patterns. Basic necessary inputs include the inlet and the outlet pressure. Most times when you're dealing with the pipeline in ICs, you just need your inlet pressure. It will help you to get your outlet pressure because along the pipe, yes, there's going to be a pressure drop. So it helps you to calculate that. All right, depending on the kind of terrain it's going to be flowing through. And then you have your mass or molar flow, which is also important. Then the pressure drop is particularly complex, affected by thermodynamic properties of all mixture components, their interactions with each other, and interaction with pipe material at the interface. So this is just the step guide for each of them. For key factors to look at, we have the inlet and outlet pressure, which is one, your mass and molar flow, another one, your flow geometry, that is your pipe diameter, the length, configuration. All of this affects the behavior of the flow of the gas. And then your pressure drop, which is usually complex, and this is based on the terrain or the thermodynamic model they are using, as well, or the type of part material you're also making use of. So these are key things to take note of when designing your pipeline. Now we come to line sizing process in HYSYS. Now line sizing in HYSYS determines the appropriate diameter or size of piping systems to safely and efficiently transport fluid, gases, liquids, or multi-phase mixtures from one unit operation to another. All right, this process calculates pressure drop, flow velocity, and ensures pipe capacity matches required fluid flow. So to perform line sizing, first ensure a material stream is fully specified. That's one thing. Your material stream has to be fully specified. It's very, very important. Then access the line sizing tools through equipment design or stream attachment. We're going to be doing all of this in HYSYS. And finally, attach a stream to the line sizing manager, which is what we're going to be looking at in HYSYS. Then you input the parameters, which includes your piping material, the schedule, and the length. Then you design the design criteria such as the maximum pressure drop or the velocities are then given to the line sizing manager, and then HYSYS will help you to calculate the pressure dimension, the pipe dimensions, all right, needed to transport that particular gas. All right, so these are just the key steps to follow. Specify your material stream, you access the sizing tool, the input parameters, which includes your pipe schedule, your length, and then the pipe material. And then you also input the maximum pressure drop and the velocity limit. And then HYSYS will calculate the dimension of the pipe for you. All right. So now line sizing involves a trial and error process to find a pipe diameter that meets both velocity and pressure drop criteria for a given flow rate and fluid. So usually the general formula is the flow is equal to the velocity times the cross-sectional area. All right, where the area is calculated using the pipe internal diameter with the formula, that's the area of the pipe, which is pi d square, where your d is your diameter all over 4. All right, and this calculation often use a preliminary diameter based on the maximum velocity and then checks the resulting pressure drop against design limits. All right, so um, usually whenever you're trying to calculate the the appropriate size of the pipe that should be used, most times it's always advisable to make sure the velocity of that pipe is less than 25. Sorry, the velocity of the gas that is being transported is less than 25 or equal to 25 meters per second. All right. It's usually advisable to keep it within that range, less than or at 25 meters per second. All right, it's very important. That's another key thing. So remember, we said this is a trial and error method. Most times you try with different pipe schedule and size. All right. Once you do that, once you calculate it, you get the velocity. If it's above 25 meters per second, definitely you know that that size cannot work for the transportation of that particular gas you're trying to deal with. So you need to increase the size of the pipe and then see how to maintain the velocity less than or equal to 25 meter per second. All right, so this is one of the key things to put at the back of your minds whenever you're trying to design your um, pipe size. All right, so it needs to be able to accommodate that velocity. All right, so um, this is what your line sizing manager on HYSYS looks like. You can see where we have the pipe material. You can see for this one is carbon steel. You have your pipe schedule. We have different schedules. We have the schedule 40 and the schedule 10. But what this schedule means is it holds different diameters of the pipes. All right. So some of them, the schedule might be for a larger size. Some might be for smaller sizes. It all depends. But most times your schedule 40 it holds a very a lot of sizes. All right, it holds a lot of sizes in it. All right, from small um, to a large amount of diameter. All right, so that's what your schedule is all about. You have different schedules. All right, so we're going to be seeing this in Aspen HYSYS soon enough. And then now let's quickly look at flow assurance and risk management. So your flow assurance encompasses the thermal hydraulic designs and assessment of multi-phase production fluids through pipelines. It involves prediction, prevention, and remediation of flow stoppages caused by corrosion or erosion of pipe materials, unstable multi-phase flow, or blockade formation, either physical or chemical, such as the hydrate formation, which is what we're looking at. So the flow interruptions can disrupt the production and damage processing equipment, costing refineries millions of dollars in lost revenue. The key to reliable pipeline is ensuring continuous flow from production to processing site at designed flow throughput. Now, your flow assurance and risk management is to help you to predict and prevent certain things that could cause problems to your piping, to your pipeline. All right. Some of these things are the erosion, corrosion, the slugging, which we saw earlier, and the hydrate formations. So these are the things that could actually affect your pipeline. And once this happens, affects your pipelines, you have to replace that particular equipment, and then yeah, you have to replace the equipment. All right. So and replacing such equipment could lead to um, loss, revenue loss. All right. So it's very important that we try as much as possible to maintain our flow of gas in a pipeline at a certain temperature, pressure to prevent some of these things. So we need to observe when we're going to be likely having corrosion, erosion, hydrate formations, and slugging occurring in your pipeline. All right. And then we thank God for Aspen HYSYS, which they've been able to create a very good software that could help us predict when such things are going to happen. All right. And be able to make well informed decisions when we are designing our pipelines. So we have the flow assurance definition, which is the thermohydraulic design and assessment of multi-phase production fluids through pipelines, prevention strategies, and economic impacts. All right, so now let's look at hydrate formations. We've talked about a lot of things. We've mentioned hydrates. Um, so now let's look at what is this hydrate all about. All right. So hydrate formation in pipelines occurs when water molecules trap gas molecules like methane, ethane, or propane in a cage-like solid crystalline structure under high pressure and low temperature conditions. So most times your hydrate forms when water is present and then some hydrocarbons such as your methane, ethane, propane. We still have some things like nitrogen, CO2. When all these things are present, all right, it causes a crystal structure to form. All right, most times it might look like ice, but it's not really ice. It just forms a crystal structure, and then this could actually block your pipes once this is being formed. Okay, So when this is formed, it could block your pipe, which could cause equipment damage, production loss, and safety hazard. So we need to try and um, observe the operations of this pipeline, all right, because most time this happens under high pressure and low temperature. Okay, under high pressure and low temperature, that's when these hydrates are formed in your pipeline. So it's important to know when are you likely going to start having hydrates being formed in your pipeline so that you can make informed decisions to prevent this from happening. All right. So the hydrate formation in pipeline requires three conditions to exist. The first one is the right combination of temperature and pressure. So you need high pressure and low temperature. All right. Another one is the second key condition is the hydrate formers. They must be present. So hydrate formers are the hydrocarbons mentioned above, which is your ethane, and propane, as well as the third one, the third condition, which is a sufficient amount of water. All right, the water doesn't have to be too much, and it could actually form hydrate. So these are the three things that are required for hydrates to be formed: the right combination of temperature and pressure, the hydrate formers, which is your um, hydrocarbons, and then a sufficient amount of water. So with these three, you have hydrates formed. Now, the conditions that enhance the formation of hydrates. The first one is turbulence. All right, this can be either due to high velocity or agitation of the processing of the process fluid. So high velocities in pipelines can occur at a sudden restrictions in the line, such as a choke valve, and then gas flow, a large pressure drop across the choke valve causes the temperature to drop due to the Joule-Thomson effect, which favors hydrate formation. So whenever we have turbulence, have high velocities going on in your pipes, this could lead to um, hydrate being formed. All right. Another one is the nucleation site. In general terms, the nucleation site is a point where a phase transition is favored, and in this case, the formation of a solid from a fluid phase. So new good nucleation sites for hydrate formation include an imperfection in the pipeline, could have like a weld spot or a pipeline fitting, which could be the elbow, the teeth, or the valves, slits, scales, dirt, sands. They all make good nucleation sites as the well, all right? Then you have free water. Free water is not necessary for hydrate formation, but the presence of free water certainly enhances the hydrate formation. All right, so these are some of the conditions that enhances the hydrate formation. So HYSIS uses a utility card, which is the hydrate formation utility, which prevents the hydrate formation temperature of any defined stream for a given stream pressure and the hydrate formation pressure for a given stream temperature. So what this does, it observes the temperature and the pressure, and then it sees where or at what point are you going to have hydrates being formed in that particular stream, especially when designing the pipeline for that stream. All right, so to model the hydrate formation in pipeline in HYSIS, you must first define the fluid package. Remember, I talked about fluid package, your equation of state, and most times for this particular simulation, we are going to be using the Penn-Robinson equation of state and the stream properties, which includes water and other components. Then you create a pipeline model and use the hydrate formation utilities or hydrate analysis feature to determine the hydrate formation temperature at various pressure and temperature conditions along the pipeline. The simulation predicts hydrate formation to actually if the actual stream temperature is below the calculated hydrate formation temperature. So now let's look at hydrate prevention. All right, so how do we prevent hydrates from being formed in your pipeline? The first one, which involves the removal of water. All right, these are ways we can prevent hydrate from being formed. We can remove the water, removal of water, alter the temperature or pressure, or use chemical inhibitors to stop solid ice-like crystals from blocking the flow. Using methods like glycol dehydration, injecting methanol or glycols, or applying low dosage inhibitors to disrupt the hydrate formation under high pressure and low temperatures. We are going to be seeing how some of this works very soon. Um, we have the water removal. All right, so this is usually like a glycol dehydration, TG. See that you first have to process the gas, remove a sufficient amount of water from it. Then we have the chemical inhibitors, and this things like your methanol, things like your um, monoethylene glycol, that's MEG. You can also make use of this to prevent hydrates from being formed. All right, so that's chemical inhibitors. Then you have the operating condition control. Remember, low temperature, high pressure causes the formation of hydrates. So you need to alter this operating condition so that you don't have hydrates being formed. Then you have your heat conversions. So your insulations for subsea lines. All right, insulation helps to retain heat, keeping the temperature above the hydrate formation conditions. All right, so these are part of the ways to prevent your hydrates from being formed. All right, so before we quickly go into the simulation, all right, we can take question for just 5 minutes. Any question so far? All right, so I think we don't have any question. Any doubt? All right, so if you understand what I've been saying since, you can just give a thumbs up, you can drop a thumbs up, and then, all right, just drop a thumbs up. Yeah, drop a thumbs up. Are the slides going to be shared? Oof. All right, we can consider dropping it in the group chat. All right, yeah. Okay, so I believe we all understand what we are trying to do and what we're trying to achieve. So now let's quickly go into the HYSYS software. I'm making use of the version 12, sorry, 14. All right, making use of the version 14. And okay, so part of the things we are going to be looking at is simple gas gathering process. I believe some of us might have seen this before, but if you've not, well, we're going to be dealing with a gas gathering process because this is one of the best ways to explain to you how gas is being transported. All right. And then there are some things you have might have seen. I don't know, some people might have gone through YouTube seeing different videos, but there are some things you need to understand with this process of gas gathering, which we are going to be dealing with today as well. And let's just wait. Yeah, okay, someone's hand is raised. Yeah, yes, Sid, I can see your hands are raised. Any question?
Hi, sir.
Yes.
Is it an exercise or what should we do?
All right, so it's going to be an exercise. Just we're going to go through it together. I'm going to show you how it's being done, so you don't need to bother too much.
Okay.
Yeah, okay, I'm coming. Okay, all right, so all right, so we're going to start with a new case. I believe everyone can see my screen. All right, so we're starting with a new case, and then I'm just going to create one, create a new case. Okay, so let's. All right, so in this example of gas gathering, we have different gas wells located at different production wells, different sites. So you see we have well A here, well B, well C, well D. All right, and then yeah, so this is going to be transported over an area of 2.0 square kilometers. All right, connected to gas plants via a network of pipelines. So we have different pipelines, all right, different pipelines, and then they are taking it to the gas plant. Now, the main idea of this is that this is where geologists and chemical engineers come into play, all right, because to interpret this particular pipeline, you also need geologists, all right, because these are the ones that will tell you how the terrain is like, all right, they tell you how the terrain is like, what elevation are you going to be having, what depression are you going to be having, and then you'll be able to input all of this into your HYSYS model. What we have here is a um, topographic map, all right, and then these lines you see here, they are usually called contour lines, all right, for some of us that did geography um, in high school or in the college, yeah, in high school, we call it in high school, yes, or secondary school, we call them secondary schools in Nigeria here. All right, I believe it's high school in overseas, all right, other places they call it high school, we call it secondary school. So people that do geography, you should know that yes, these are called contour lines. This is your topographic map, and then this is how the gas is supposed to be transported, and these are the pipelines. These dark lines here are the pipelines. All right. So let's quickly get to it. Let's get our components and then we move on. So let me split my screen. Okay. So let's quickly add the components. We're going to start with methane, ethane, propane down to n-hexane. All right. So let's just add that. Um, this C7 plus is supposed to be a hypothetical component, all right, but I'm just going to add heptane for it to represent that, all right, but it's supposed to be a hypothetical component. That's why we have this molecular weight here and the liquid density for it. All right, so these are the key things to define this particular C7 plus here. But I'm just going to use the heptane for it for this particular web now. All right, so just going to add all of this. If you want to learn how to make use of hypothetical components, you're likely going to join our classes, our trainings, because we go into details on that. All right. So heptane. So we need to add nitrogen, CO2, and H2S. So N2, nitrogen, CO2, and H2S. All right. Okay. All right. So we've added all the components we need. So we've added all our components. Now the next thing we need to add is our fluid package. And your fluid package is going to be Peng Robinson. All right. So we are going to be using the Peng Robinson for this. And now let's quickly add our streams and yeah. So go to simulation. We're not going to add water yet. After we are done with the simulation, we're going to add water and then hopefully an inhibitor to see how this is going to affect our pipeline, especially when it comes to the hydrate formation. So I'm just going to quickly start by adding 4 streams. All right, and then these 4 streams would represent our different gas wells. All right, so you can see we have well A, well B, well C, and well D. So I'm just going to call them, well A is going to be my gas well 1. All right, and then let's quickly get the specifications for this. Okay, so from what we have here, all of them are using the same mole fractions, all right? They have the same composition. That's what we're going to be using for all of them. So let me just add the composition for this. So we have 0.623, same is 0.28, 0.0163, 0.00433, 0.00821, 0.00416. We have N-heptane 0.00405, N-hexane 0.00659. We have N-heptane, yeah, 0.00992. Then nitrogen is 0.00554, and then CO2 is 0.0225, and I-pentane, okay, sorry, hydrogen sulfide, that is 0.0154. All right, so after you add your mole fractions, all of these have to be equated to 1. All right, so If you are defining your flow rate in mole flow, it's advisable to give your fraction in mole fraction. If it's going to be in mass fraction, it's advisable to give it in mass mole. If it's going to be in mole flow, if your flow rate is in mass flow, sorry, your fraction should be in mass fraction. If it is in mole flow, your flow rate, your fraction should be in mole fraction. So these are some of the things we just need to note, all right, when designing with Aspen model, Aspen ICs. The next thing we are going to look at is our temperature, pressure, and the flow rate. So the flow rate here is in mole flow. You can see kilogram mole per hour. So we just go back to conditions and then put in the temperature for gas for 1, which is 40. We have a pressure of 4135 kilopascal, and then the mole flow is 425. Okay, so with that, then we go forward. All right, so you can see this is fully defined. This stream is fully defined. That's why you have this indicator here showing OK. All right, so and then you can see that this is having a deep blue on it compared to this one, which is lighter blue. So the next thing we are going to be doing is defining the remaining gas wells. So remember, they are all having the same um, they are all having the same flow mole fraction. So I'm just going to name this gas well 2, which is your well B. All right, and then I'm going to call this, okay, the temperature for this one is 45 degrees Celsius. We have a pressure of 3450, and we have a mole flow of 375. Now we need to define the composition. Because I've defined it in the first one, I don't need to start imputing the composition again. All I need to do is go to define from stream. I'll select my gas well 1 and then take off this, take off all of this and just select composition. So this is copy stream condition from gas well 1 and I'm sending it to gas well 2. All right, so with that, you can see the indicator is showing OK, meaning that this stream is fully defined and ready for use. Now I'm going to define the third one. All right, okay, I'm going to define the third one. I'm just going to call this gas well 3. Okay, and the temperature for this is 45, and the flow rate is given as 575. All right, so what I just need to do now, I'm going to make use of the pressure or gas well 1 for my gas well 3. All right, just so to do that, select the composition and pressure from gas well 1, and I'll use to define this, and then let me do the last one. All right, so this is gas well 4, and the temperature there is 35, and your flow rate is 545. All right, then your composition, okay, we're just going to use the pressure from gas well 2 to define this. So what to just do here, define from stream, and then yes, gas well 2, pressure and composition, click on OK, and we are good to go. All right, so now we have our 4 wells defined. Now let's start with our pipes. So the first one we are going to be making use of is the branch 1. which is for gas well 1. And then this is the branch here. All right. And for this branch, we are having 3 segments. All right. So from here to here is segment 1. From here to here is segment 2. And from here to here is segment 3. All right. So these are the sections along this pipeline. All right. So we're going to be having 3 segments for branch 1. All right. So let's quickly add that. Let's get our pipes. So we have pipe segment. All right. So we just put this here. And then we name this branch 1. Our inlet is going to be gas well 1. And our outlet is going to be B1 out. That's just to represent branch 1 out. All right. And then your energy stream, which is compulsory, we will just name this B1Q, which is branch 1 energy stream. Okay. Now we go to ratings and then we add the segment. Now for this one, we have some specifications for, remember we have 3 segments here, and I've explained to you how this segment looks like on the map. So, all right, so this is branch 1, segment 1, 2, and 3. All right, so we have for segment 1, segment 1 here, the length is 150. So we have 150 meters, and then you have an elevation of 654 meters, but then is the elevation change we are going to be making use of, which is 6 meters. So we have elevation change here, 6 meters. Now to select the diameter, now this particular one has already been calculated and then they've already gotten the size of the pipes. All right, so we just come here. This is the diameter here, 76.2. So you see, you can double click on the outer diameter and this will come up, or you go to view segments and you have this diameter come up. Now, this is the actual size. If you have the actual size of your pipe, all right, you can, based on the calculations you've done, and you have an actual size, you can actually give that information here, just impute it under actual. All right, and then remember I talked about different schedules, schedule 10, schedule 20, schedule 30, schedule 40. All right, and each of the schedule has different diameters. Now, this is schedule 10, for example. The nominal diameter you can see from 350 to 900 millimeters. All right, that is the diameter. You see that it's quite high. Schedule 20, you see this is from 250 to 900. You have schedule 30, and you can see this is from 200 to 900. And then now you have schedule 40, which actually contains the one we want to make use of. Now remember our schedule is 76.2. So see we have from 6 to 900. All right, so we're going to make use of schedule 40, and we don't have 76.2, but we have 80 millimeters. So most times you just go for the next one, all right, the next size to the actual diameter that was given here. So we just go to 80 millimeters, and then you can see the inner diameter is 77.92. All right, and we close this, so you can see outer diameter it's 8.90, inner diameter 77.93. Okay, now we need to add 2 more segments. So I'm going to click on append segment. Click on it twice so that we can have segment 1, 2, and 3. All right, so let's add that. So the length of this is segment 2 is 125. Elevation change is minus 8.5. Now on the map, all right, the elevation is 654. All right, that's where this first segment is. Now the difference between this elevation here and the next one This negative sign represents a depression actually, not an elevation. Positive sign is for elevation, negative sign is for depression. So now on the map, there is a depression. That's why we have a change on the map. And you see this is 636.5. All right. And then you can see that is minus 8.5. So if you do a subtraction here, you see we have minus 8.5. All right. So that's where this elevation change came about. And then the diameter, in the case of schedule 40, and then still make use of 80 millimeters. And then for the last one, this is length of 100, and then still making use of schedule 40. Diameter is 80 millimeters. All right, so you see from the notification bar here, you have heat transfer information under specified. So we go to heat transfer and we are making use of estimate HTC. All right, so we have, all right, so you can see schedule 40 pipes are used throughout and all branches are buried at a depth of 1 meter. All pipes are uninsulated. Consider inner and outer HTC and the pipe wall in heat transfer estimation. We have an ambient temperature of 5 degrees and then the calculated pressure drop and heat losses inside each branch. So you can see this pipe is buried at 1 meter. All right. All right. This is, you can see, you can select the ambient medium. Is it air? Is it ground? Is it water? All right, but this is on land, so we keep that as ground. Ambient temperature is 5. We include inner pipe wall, so include the pipe wall, inner HTC, and outer HTC. And then you said there is no insulation, so we don't tick this. And then you see that your pipe is ready for use. All right, so that is for branch 1. So let's quickly do branch 2, 3, 4, 5, 6, and 7. I believe it could be done in the next 15 minutes. All right, so let's see. All right. Okay, so gas well 2, I'm going to call this branch 2. All right, and then we call this B2 out. And I'm going to call this B2Q for my energy stream. Okay, so let's quickly go to ratings and let's put in the necessary specifications. So this is B2. You can see it's just a single branch. We don't have any demarcations in between. So we have just one segment, and then I'm going to append just one segment, and we have a length of 200 with elevation change of 23, and then branch 2 has a diameter of 101.6. So schedule 40, and we are going to be using 100 for this one. Okay, and then we go to heat transfer using the same data. Just make this 5 degrees Celsius, and then all right, so this is solved. Now let's quickly go to branch 3. So let's check branch 3 so that we add it appropriately. So this is branch 3 for gas well 3, and then you can see we are having 3 segments as well. So from here to here 1, here to here is 2, and here to here is 3. All right, so we have 3 segments on this particular branch. All right, so let's quickly add that. Pipe segment. Gas well 3, branch 3. And then we call this B3 out. And we have energy of B3Q. Okay, so segment has been added. Sorry, this segment added. So add 3 segments. So let's quickly give the specifications for the 3 of them. So the first one has a length of 160 meters. The second, okay, it has an elevation of 12.5, and the diameter for this one for branch 3 is 76.2. So we're going to make use of 80. So schedule 40, diameter, nominal diameter 80. All right. So we have branch 2, which is 100 length. We have elevation change of minus 14. So that's actually a depression going on there. And then we have the outer diameter, nominal diameter, schedule 40, 80 millimeters. So, okay. And the last one is 205 with a depression of minus 1. And then we have, okay, schedule 40, 80, and yes. All right, so let's quickly give the heat transfer estimate. All right, and this is 5. All right, so now you can see that we have increment dp, as the change in pressure is greater than 10%. So usually this happens in your underperformance. If I check the profile, usually the dp is not supposed to be greater than 10% of the pipe. All right, so once you do an addition, it should not be greater than 10%. All right, so that means the pipe is too small for the amount of gas you're trying to transport. So usually what you just need to do in such situation is to increase the size of the pipe. So I'm going to increase the size of the last one. All right, so I'm going to go to just 90, and then yeah, so this is okay. I'll be explaining this better in a bit. So let's quickly do some add-ons. So we have branch 1. All right, so we're going to connect this real quick. Branch 1 and branch 2. This is a junction 1 here. You just make use of the mixer for this. So just going to call this junction 1, and then my outlet is going to be J1 out, and my inlet is B1 out. Remember, we're connecting branch 1 and branch 2, B1 out and B2 out. And we close this. Then we quickly add the branch 4 here. This is branch 4. So I'm just going to add this. That's another pipe. Okay. So this is J1 out coming in here. And then this is branch 4. Okay, and then we call this B4 out. All right, and the energy here is going to be B4Q. So just quickly put in the pipe segment. This is just one from here to here. It's just one straight line, no other segments in it. So we just append one segment and then we add the specifications for this. So we have a length of 355, an elevation change of -4, and this particular segment should be 101. Yeah. So schedule 40, we make use of 100 for this. All right. So heat transfer, keep this on 5. Sorry, estimate, go to estimate HTC. Keep this on 5. And then we are good to go. So the next thing to add is your okay, let's quickly, so we need to combine branch 4 and branch 3 together. So this is junction 2. So let's quickly add another mixer to this now, representing junction 2. Okay, so this is junction 2. All right, and then we add B4 out and B3 out, and we call this J2 out. That's junction 2 out, and I think this should be ready for us to use. Close this. All right, so we've been able to add that. So now let's quickly add branch 5 and then branch 6 and just deal with branch 7. So branch 5 is also a single segment. You can see there is no division going on in here. We just have no segments, just one straight line here. So we add one pipe, another pipe here. So we're going to call this branch 5. Branch 5. Our inlet is going to be J2 out, and we call this B5 out, and this is going to be B5Q. So we quickly add segment to it. Remember, it's just one. So this is branch 5, and then we have length is 300. Yeah, length is 300 meters, and then we have elevation change of -16, and then we have an outer diameter. I think this should be 152. So we just make use of schedule 40. I think we should be able to use 150. Yes, we use 150 for this. And then we specify ambient temperature of 5. All right, so this stream is ready. Now let's quickly add the last one. Okay, last two actually. Still have two more to add. So we have not done that of gas well 4. So let's quickly check gas well 4. So gas well 4 has two segments. So from here to here is one segment, from here to here is another segment. So we're just going to make use of two segments for this. Okay. So we add the pipe. So this is gas wall 4, and we call this branch 6. Okay, and then we have the outer diameter for B6 out. Okay, and the energy stream is going to be B6Q. All right, so let's quickly add the segments. Remember, this is having two segments. So segment 1 and 2, and then let's give the specifications for these two. All right, so this is branch 6. So the length is 180 for the first one, and then we have elevation change of minus 7.5, and this should be one, let's see, branch 6 is also 76.2, so schedule 40, I will make use of 80. Um, so the length of the segment 2 is 165 meters, and elevation change is minus 8. So change this to schedule 40 and then making use of 80 here. So now we quickly go to the heat transfer, and then we add 5 here. So this is not solved. We are likely going to have to increase the pipe size. All right, we're going to increase the pipe size, right, because this cannot accommodate it. Let me check on the performance. Let me quickly look at the velocity. I think those are part of the things that affect. Um, okay, so you can see vapor velocity. We are having something above 25. Is 25.7. Remember, I said we should try and keep everything under. So I'm just going to increase the size of this pipe here. Under rating size. So we're just going to increase the outer. All right, so let's go to 90. All right. So let's go back and check. You can see vapor velocity is less than now. You can see that 22. The highest we're having is 22.6. So, all right. So I'm going to close this. All right. So let's quickly add the third junction and the last and final branch. So this is junction 3. It's going to be with the mixer. Before I proceed, let me save this so that, because sometimes it's always advisable whenever you're working with ISIS, try and save your work, because sometimes anything can happen and you could lose it. So I'm just going to put web 2 for this as webinar 2. All right, so yeah, let's quickly. So I was about to add junction 3. Move this forward. Okay, so B5 out and B6 out, and this is J3 out, because this is called junction junction 3. Okay, so I'm just going to close this, and then we add the final branch, which is to the gas well. Let me add this here. All right, so you can see we have just a single, no division in here, just a single segment. So we call this branch G3 out. That's our inlet. Our outlet, I'm just going to put to gas plant. All right, and then energy stream. This is branch 7. Okay, so we call this D7 out. All right, segment added. Just all right. Can everyone hear me? If you can hear me, give a thumbs up. All right.
Yes, sir.
Okay. All right. So let's go on. So we have length for this branch 7. All right. So the branch 7 here is 340 meters. And then we have elevation change of minus 13. And I think this should be 152. So make use of 150 here. What's this? So let's deal with the heat transfer. 5 inner, outer.
Sir,
Sorry.
could you explain what the reason of ambient temperature we choose? You have choose 5 degrees Celsius.
Yeah.
What the reason of this uh, choice? I think
All right. The reason for the choice of the ambient temperature is due to the surrounding of where the pipeline is passing through or is being transported through. All right. So for this particular one is transported 1 meter below the ground, and then the ambient temperature surrounding the pipe. All right, because definitely they would have taken measurements and then checked the temperature around the pipe and everything, and then it was discovered to be 5 degrees Celsius. So that's why we are making use of this. It all depends on the terrain you are using. All right, so if it's underwater, it could be less than this. If it is above the ground level, it could actually be above the 5 degrees. It all depends on what the geologists have done. All right, and then they'll give you the specifications on that. All right, does that answer your question? Okay, so let's move on. So now we're having increment delta P, so we just need to increase the pipe size here real quick. 150 cannot accommodate this, so we go to 200, and yeah, so this is fully solved. So now let's quickly look at hydrate formation and see how we can also prevent it. Try to touch that within the next 9 minutes. All right, so I'm going to use, all right, let me, since we are done with this PDF here, so all right, so this is what we have. Okay, so let me just use branch 5 as an example. All right, so now when you want to do or check when you're going to be having hydrates being formed, remember we talked about the flow assurance here, so this is it. So you click on flow assurance, You can do other um, analysis, corrosion, erosion, but our major focus here is hydrates. So we go to hydrates and then we click on do hydrate profile calculation. All right. So this is your temperature profile across the pipe length. So across the pipe length, this is the starting temperature. You can see that in our worksheet, this is starting at 34.82 and it's coming out at 32.77. So you can see there was a temperature drop there. All right. So this is what this red line here represents. And then this blue line here represents your hydrate formation temperature. So this is our current temperature and this is the hydrate formation temperature. Now you see that it occurs at low temperature, right? Remember from the explanation we gave, low temperature, high pressure, that's when you have hydrates. These are part of the conditions required for us to have hydrates being formed. So we have the hydrates temperature here. So if our temperature is below this temperature, this blue line here, that is below 11.85 or 84, we are going to have hydrates being formed. There's a likelihood of hydrates being formed. This is for temperature profile. We can check for pressure, and then you can see that for pressure, this is the hydrates formation pressure. All right, so anything above this, we are going to be having hydrates being formed. All right, this is our current um, pressure line. All right, this is the current pressure line. All right, so I can check this for other pipes as well. Let's check this one, branch 4. Just come here, hydrates. Okay, so you can see for this one, it needs to be at 14.32. So any temperature below 14.32, you're likely going to be having hydrates being formed. And then you also, this is our current temperature profile. All right, this is the current temperature profile. You can check that for the pressure as well, and you can see the pressure here. This is the hydrate formation pressure. All right, so yes,
Sir, I have a doubt.
okay,
As you earlier said that for hydrate, uh, it requires moistures. But in streams we mentioned there is no moisture. So how hydrate will form?
yeah, I'll come into that. We have not done that yet. Right now, we don't have any hydrate being formed in our pipe. Okay, we don't have any hydrate being formed at the moment. I'm going to show you that too, because of all the conditions have not yet been met. Now, I'm just trying to show you the temperature and the pressure where you're likely going to be having hydrates being formed in your pipe. Remember, these are part of the key conditions required for us to have hydrates being formed. All right, so um, for this pressure here, okay, let's look at this stream for example. Let me just quickly show you this stream here. I'll just go to attachment, analysis, create. Let's check the hydrate formation. And then you can see that for this stream, on the current conditions we have, all right, you see we will not form. And even if we are supposed to have hydrate being formed on this stream, it's going to start with the ice form first. That's a different type. We have different types of hydrates in Aspen hyces here. We have the type 1, type 2, type H, and so. So for this one, for this stream right now, it's saying hydrates will not form. All right. So with all the conditions, hydrate will not form on this stream. I can also check B6 out. Let's just quickly look at that. Create and then hydrate formation. You can see will not form. On this stream, it's not going to form because of the conditions currently. Now I'm going to show you when we are going to have hydrates formed in our streams. Um, all right, I know our time is precious. This was supposed to end by 5:30. We have 3 minutes to 5:30. I want to ask for 15 more minutes. If we all agree for 15 more minutes, I can go on. So that are we all good? Can I take more time? I need more show of hands. I'm just seeing few people. All right. Okay. Thank you all. So let's add 15 minutes to it and let's get to it. So now I'm going to add two things. I'm going to add water and an inhibitor to it. The inhibitor I'm going to make use of is methanol. All right, so I'm going to be adding these two components. So I'm going to start with
Hello.
N2. Oh, yes.
Yeah, whether this PDF and this recordings along with simulations file will be shared or not
Um, okay, I'm going to share
for
it.
practicing.
I'm going to share it. I'm going to share it.
Okay, okay. Thank you, thank you.
All right. So I've added water to it, and then we have the last thing is methanol, which is supposed to be our inhibitor. All right, so I'm going to add methanol to this. So I'm going to go back to the simulation environment, activate. All right, so let's go. So now in our stream, let me make use of gas or 4. All right, so for this one, I'm going to go to composition, and now I'm going to add water to it. All right, so let's just say we have 0.04. Okay, I'm just going to normalize this, and so now we have water in this stream. Okay, I've not added methanol to it yet. All right, so we just have water in this stream. So now let's check something. So this is branch 6. Let's check the flow assurance, hydrates, do hydrates calculation. So now it's telling us that this is the current temperature profile. All right, this is the red one here is the current temperature profile. And then for us to have hydrates to be formed, we need to have the temperature below 15. All right, temperature has to be below. Okay, this is yeah 14.5 actually. It has to be below 14.5. So now this is what I'm going to do. I'm going to change my gas wall 4, the temperature for gas wall 4 to 15. Okay, and then now we check our. All right, so now you can see that we have hydrates being formed. You can see that once the temperature crossed the hydrate formation temperature, we started having the type 1 hydrates being formed, right? Yeah, that's type 1 and 2 actually, because this is the legend for type 1 and 2. So we have, okay, it's type 1, sorry, just type 1. So we have the hydrates being formed. Now, if I go to this stream here and check the analysis, you see that we have hydrates. Initially, it said will not form, but now we have hydrates being formed. You can see that hydrates will form. Okay, so now the next thing we need to look at is how do we prevent hydrate formation? Now, we talked about using methanol, all right, as an inhibitor. So now I'm going to add a little bit of methanol to this stream. All right, so I'm just going to add methanol. Let's say I add about 0.02 to it. Just going to normalize everything. Yeah, click on OK. Now we can check. You can see as I added methanol to it, you can see it will not form. So methanol has been able to, what methanol does is it drops the hydrate formation temperature. Remember initially the hydrate formation temperature was about 14.5. This is still branch 6. But after we added methanol to it, you can see that the temperature has dropped to minus 11.46. That's when we are going to have hydrate being formed based on the fact that we have methanol. So it dropped the temperature. All right, so these are some of the things we need to take note of when we are dealing with pipe um, pipe analysis. All right, flow assurance, pipe analysis on hydrate formation. So now with this, I've shown you how hydrates are being formed and also how you can prevent hydrates from forming. All right, so now let's quickly go to line sizing, which is the final thing for today. All right, so let's go to line sizing. So I'm just going to work on this to gas plants. Let's just say we want to add another pipe to this. All right, so now to do that, we're going to double click on this. We go to stream attachments, we go to analysis, create, and then we come to hydrate formation, sorry, line sizing, add line sizing manager, and then we have this. Okay, so we already have the pipe material selected, we have the schedule selected. All right, now we need to know the diameter of the pipe that we're supposed to use for this particular flow, and then all right, the length as well. I'm supposed to give the length. So now let's say this particular pipe is supposed to move over 100 meters. All right, that should be the pipe length, 100 meters. And then for us to size this pipe properly, you go to settings. Now you can either put the maximum pressure gradient or the maximum velocity. Now remember we said we have to keep the velocity below 25 degrees Celsius. And also when you are dealing with your pressure gradient, it shouldn't be greater than, that's the temperature, the pressure drop shouldn't be greater than 10% of the entire pressure. All right, so let's check, let's start with the velocity. So for this one, remember we have to keep it below 25. So I can just say this is running at the velocity of 24. All right, and with this, we would be able to get a length. All right, so you can see we have, this is the diameter that we should use. This is the recommendation from HYSYS. We should make use of diameter of 200 millimeters. All right. Also, we need to, I can add the pressure gradients for more accuracy. So let's look at this particular. Okay, we have 210. So 10% of 210 here. Sorry, 2110. 10% of it is going to be 211. And then when we talk about the maximum pressure gradient, this is the pressure gradient per meter. All right, so since we're having 211, I'm just going to um, I'm going to say 100 divided by 211. All right, 100 divided by 211. and that's going to be 0.47. So I'm just going to put 0.47 here because remember the full length is 100 meters, and then for us not to have a temperature or a pressure more than 10%. All right, remember we found the 10%. This is just an assumption work here right now. I would advise you, I will give you a link of a YouTube channel you can actually watch to help you with more about these calculations. All right, that is you can jot that down. If you go to YouTube, you can search for velocity of gases under simple science. Yeah, they will help you with sizing of pipes as well. All right, but this is just um another way to go about it. All right, so you have a length of 100 meters, and for us not to go above 10% of the pressure, its pressure drop should not be 10% more than the actual pressure. All right, going in. So we divided the length of the pipe divided by 10% of the pressure going into system, and then we're having 0.47. So once I put this in, I go to sizing. All right, you can see that it is. All right, so this is still giving me 200. I can still make use of 200 for this. So with this information, I can add a new pipe. Let's add this. So from what we have now, the line sizing we just did, it gave us 200 um, millimeters as the diameter of the pipe. So that is to tell us that anything we are doing with this new pipe we're giving should not be below 200 millimeters. All right, it shouldn't be below 200 millimeters. So I'm just going to call this let us say gas plants. All right, let's put gas plant. And then I'll say GP as gas plant here. So I'm just going to append just one segment, and then my length is going to be 100. Remember that was the length. We are not going to have any elevation change, and I'm going to select my schedule. Let's start with 200 first. All right, estimate H2C. This is going to be 5, and then include all of this. So you can see how I was able to size this particular um, pipe, all right, making use of the line sizing manager. So with the aid of the line sizing manager, we are able to get this. All right. So any question so far? All right, I have a big announcement to make. So let's quickly take in the questions and then I'll make a big announcement. Any doubts? If you enjoyed the session, can give a thumbs up, can clap. Anyone? All right. Any question? Any question? Any doubts?
Yes, thank you very much for the good session. I have one question.
Okay.
Can you please check now the last pipe, which is now shown as pipe 100? How much
Okay.
is now the delta P? Delta P after the modeling. The one delta P we put by criteria, and now I want to see that what is the calculated delta P.
Okay. So let's quickly. All right.
Is around
That's just about
40.
40. Yeah, that's about 40. I can still check the pressure profile. This is just across each
Hmm.
length. Yeah, this is just across each length. But the delta P across this is just 40
40 degrees.
degrees.
And our criteria was, yeah, we can go up to 211.
Yes.
Okay.
Okay.
Okay. Another question regarding when we were simulating the branches, we were putting the elevation changes only. But does this makes any difference of the elevation number itself, which was around 650, 630? There is any option to put these elevation numbers, or does only the change in elevation is only the inbox which we where we can put? Because I
Uh,
cannot see any box where we can put this elevation.
yes, it's just the elevation change you can add. You don't need to add the elevation itself. The elevation is just talking about the point where the pipe is situated on land. All right.
Hmm.
Yes, so that's where we're having maybe 648, 600 and something. That's where it is. But the elevation change, which could be an elevation or depression, all right, so that's
Hmm.
going to be the difference in the height, whether it's passing through a valley or it's passing through a mountain, depending on wherever the pipe is passing through
Yes, the
the
change is
terrain.
okay. The change
Yeah,
can make sense. But my question was specifically with reference to elevation.
yeah, you can't add that.
Okay, no. Okay, another question regarding the ambient temperature. This ambient temperature talks about the temperature in the surrounding, like in the atmosphere, or the temperature around the pipe, or the atmospheric temperature, like the weather in that area.
Okay, it's actually the temperature within the pipe and the pipe surface as well as the surrounding.
Hmm. So, but from where come this number? Because okay, for this case we have given the number in example, but normally, from where we are getting this number? The minimum ambient in that area for all the year, or the some from the ground? So just that from where exactly we will be getting this number? Who will be supporting us in this?
All right, so usually this is being done by geologists. They are the ones that actually survey the terrain, and then they would give you the conditions around the terrain. So most times the ambient temperature is going to be given to you by them, and then but for this particular scenario I'm making use of, all right, it was given as 5 degrees. It could actually change, all right, depending on the time of the year. It could actually change. Some seasons are hotter, some seasons are cold. So you would actually have to account for that depending on the season. That's why we have regular inspections going on to be able to understand the conditions at different times. Okay?
Hmm, hmm. Okay, thank you.
Yeah. All right. Any other question?
I have a question. In the interconnection point, junction point,
Mm,
which kind of pressure has been considered? Because we have two streams there. So
yeah.
the output streams, which pressure have the maximum pressure between the two streams or the minimum pressure?
Okay. So for this junction, there's a specification that is usually given for it for your mixer. So if you come under parameters, you can see this is set outlet to lowest inlet pressure. So it's based on the lowest pressure. All right, so we have B1 and B2, and then the lowest pressure is B2 out. That's why we're having G1 out. All right, so if you want to account for the two of them, you click on equalize all, and then yeah, with that, we're having some errors coming up for now. So we need to, okay, let me change this back. All right, so you can actually equalize it, but that way you'd have to do some other things to prevent the error that came up initially. And but for this one, we made use of the set outlet to lowest inlet pressure. Okay, does that answer your question?
Yes, yes.
All right.
But another question. But we have just simulated the distributed pressure loss, no? But we can also simulate the concentrated pressure drops. So, for example, valves or elbows is
If
possible.
you have valves,
Yes,
yeah, if you
valves.
have,
So,
okay, yeah, if you have valves, you can add your valves to it, and then you could also add that and check the pressure drop across that as well. So definitely there's going to be a pressure drop across the valve. All right, so it all depends. But for this particular simulation, we don't have valves attached to it. Now, if you are supposed to actually do a comprehensive simulation on this, you're supposed to have compressor stations, all right, which would also help you to boost the pressure along the transportation line. That's across the pipeline, the entire pipeline. You're supposed to have some valves, but this is just the basics, all right? This is just the basics. There's a lot when it comes to gas transportation, but this particular webinar was focused on the sizing of your pipes as well as hydrate formation. That's what we base this webinar on. Okay?
okay, thanks.
Yeah. All right. Any more doubts? Any more question? One more. Okay. So now to the big announcement. I believe for some of us, we already know that why Sims Academy is trying to host a boot camp. All right, it's going to be starting on the 24th of January. That is on Saturday. All right, we are starting on 24th, and this boot camp is focused on the HISIS user certification exam. Now we are going to be training you to be able to sit for that exam and possibly pass it once. The idea is for you to sit down, sit for it with confidence and pass it once. There is no need for you to be doing the exam two, three times, four times. No, no, no. We'll let you understand every basic concept you need to understand before taking the exam. We're going to prepare you to be exam ready. So we are going to be dealing with a lot of things. It's an intensive training. That's the HISIS user certification exam. All right. So I'm sure on LinkedIn we've seen people posting, "Oh, I just got this IC's certificate, visa certificate. I just got the expert certificate from IC's. That's Aspen Tech, sorry. So now we are preparing you to sit for this exam and be able to pass it once. All right. So this exam is starting on the 20. This training is starting on the 24th and is going to last for a month. All right, two sessions, Saturday, Sundays, Saturday, Sundays for a whole month, and it is intensive. All right, it is exam focused. Now we are going to be moving from the basics of Aspen HICs to the intermediate level. We have a curriculum that is set for this already, and then at the same time, we are going to be training you and showing you possible questions that you are going to see in the exam, and then possible simulations you are also going to see in the exam that will enable you to have an idea, take the exam and answer it and pass once. All right. So currently this training, we have limited slots. All right. We are looking at 8 students, 8 serious students. I needed to add that 8 serious students. We don't want the situation whereby you come into the program and then along the line you begin to give us excuses. No, we need 8 serious students. And because of that, we um, put the price tag at $300. All right, it's $300 for the training.
Vaffanculo, va.
All right. Um, so because of this webinar and because of just because of the webinar and since it's the first of its kind we're trying to do here, We have decided to subsidize the price by 50%. There's a discount of 50% currently. So this training now is $150. Okay. And we just have limited time. We just have from today to Wednesday, because I know Thursday, yes, from today to Thursday, because we need to see how to make install the software for some of us that don't have the software. All right. So um, at the same time, we're going to increase the slots from 8 to 10. All right, just to accommodate a few more persons that wish to enroll for this program. Some slots are already going, and we needed to add extra two to it. All right, so to be part of this, after this class, and then this discount is just going to run from today to Wednesday. From Wednesday, it's closed, and then Thursday officially the registration is closed. All right, so that we can attend to our students, help them to install the software for some of them that don't have the software, or upgrade their software to version 14, because that's what we're going to be using, and then see how to um okay, and we kickstart on Saturday. All right, so any question for now?
Uh, sorry, sir. So are you going to maybe share the link into the registration and as well as the payment?
Yes. All right, so if you want to register, you can just come into my DM. All right, chat me up on WhatsApp, and then we'll send you the link for registration, payment, everything out together in this particular link, and then we'll see how to get you on the group, and we continue with the process from there. Okay? Any other question? Remember, the slots are very, very limited. We don't want to take a large number of people, because the idea is we are really serious with this program, and we want to make sure that you know it for yourself, not just we telling you do this, do that. No, no, no. There's going to be a lot of hands-on simulations going on. So you are likely going to be simulating in this particular, it's going to be very interactive. That's just the honest truth. You're likely going to be simulating yourself, watching you do the simulation, and then if you have questions, we see how to answer it right there. You have my DM to come to any time of the day, not any time of the day, because I have sleeping hours. All right. But during working hours, you can come into my DM, ask your questions, you see how to answer your questions. And then is also a mentorship that also happens during the training program and after the training program. So after the training program, you also have access to ask questions on anything that concerns ISIS, and then you don't need to book a consultation session, or you just need to ask. Now, this depends on the kind of projects you're working on, though. But if you have questions to ask, you don't need to book a consultation program and consultation. There's a free mentorship going on after the program as well too. So there's a lot of benefits. There's a lot of benefits to this. You also get to interact with like minds in this program as well. All right. So yeah. So any other question? Any other question? All right. So I guess there is no other question. So I want to thank you all for being part of this webinar. It was a very, very interactive and interesting one. I actually enjoyed my time here. I don't know of you, but if you got value for what you learned, you can just um, put a thumbs up. Just there's a lot of information that was passed today. Lots of information. All right. So I want to thank you all for being part of this program, this webinar. So just stay tuned. You can follow me on LinkedIn. You have our um, YouTube page, Y Sims Academy. All right. Follow our subscribe to the channel, because this is actually going to be Y Sims Academy. So we already have you on the group. You can follow me on LinkedIn, and then you can also follow the company page, Y Sims Limited. We still have a lot going on in the company. So just stay tuned whenever we're having subsequent webinar, so that you know when we're having that and be able to partake in it. All right, and then other training sessions that we are going to be having. We have different training sessions in YSIMS. This one is just the boot camp. We also have others. All right, we have the basics of ICs, the basics of Aspen Plus, ANSYS, COMSOL, MATLAB. We do basically a lot of trainings on in the company here. So, and then we handle projects for you to also do corporate training. So, if you feel your company would actually need something of this sort, we are actually open to helping train the staffs of your company and then yeah, handle efficiency projects. If you want your plants to be more efficient, reach out to us. We would help you do that as well too. So that is it from me. Thank you all for coming. Thank you all for being part of this session. And then see you all next time. All right. So that's it. Thank you.